This is a Sutotal production.
Hello surveyors, this is our third practice video for chapter 6. So this one is focusing a lot on gases, and so a lot of this I'm going to relate based off the ideal gas law, right? So that's PV equals nRT, right? Where that's pressure, volume, number of moles, temperature, and then R is our gas constant. So just to kind of reiterate that, your gas constant is 0.0821, and then the units are liters times atmosphere over moles times Kelvin. All right, so your volume needs to be in liters, your pressure needs to be in atmospheres, your moles in moles, and your temperature typically needs to be in Kelvin. Now, some of these are going to relate to actual changes, but I'm going to use the ideal gas law as kind of our overarching principle. Let's remember that, and then we can kind of work our way through it. So here it says we have a 2.2 liter, so that's a volume, a 2.2 liter pressure cooker that's at 2.2 atmospheres. That's pressure, and at 85 degrees C. That's temperature, not in the correct units yet. And it wants to know how many moles of gas are in it. So the whole question is moles, right? It wants to get our N variable. So first things first, temperature is in degrees Celsius. So we need to take that 85 degrees Celsius, add 273.15 to it. And what do we get? So we get 85 plus 273.15, and we get 358.15 Kelvin. All right, now, the whole point of this PV equals nRT is that it wants us to solve for N. So let's rearrange this equation. So what we're going to have to do is get PV over RT equal to N, right? Because what did we do? We just divided both sides by RT, right, to get that. Now, so what does that mean? We're looking at pressure, which is going to be 2.2 atmospheres. We're going to be looking at volume, which is 2.2 liters. All right, and then all of that on top of R, which is 0.0821 liter atmosphere mole Kelvin. Okay, and then temperature, which we converted properly to 358.15 Kelvin. All right, so let's look at what would cancel, right? Atmospheres would cancel, right? Atmosphere on top, on bottom, liters on top, liters on bottom. So if we just look at the bottom part, Kelvin, and then below that is Kelvin. So this would give us 1 divided by 1 over moles, which that's the same thing as moles. So, right, 1 divided by 1 over mole, right, that equals a unit of moles. So when we get our numerical answer, it's just moles. It's not moles to the negative 1. So let's do this math. 2.2 times 2.2, enter, divide it by the 0.0821, and then divide that by 358.15, and what do we get? So we get 0.165 moles of our gas. All right, so that would be our answer. 2 here, you've got in a room at 23 degrees C, that's a temperature. A balloon has a volume, V, of 3.1 liters. When the balloon is brought outdoors, its volume decreases to 2.6 liters. So that's a new volume. So actually, I've got a V1 and a V2. I've got a T1, and then it wants to know the new temperature, right? It wants to know what is T2. Now, based off of this, here's something to remember. It's not... Okay, so if we use PV equals N over T, we need to isolate and get volume and temperature on the same side of the equal sign. So I would have to divide both sides by T, right? So that would give me PV over T is equal to N R. I'm done. And then here I'm multiplying by P, so I'd have to divide both sides by P. So what I get is V over T is equal to N R over P. Now, all of this is being held constant. So now I can say, oh, well, the relationship is V over T. I have to conserve whatever that is. So really what I'm getting is V1 over T1 is equal to V2 over T2, right? Because this being held constant, right, when one changes, the other one has to change accordingly, okay? So, but here's the kicker, right? With your volumes, you're fine because they're liters, but your temperature, even though it's degrees C, you need to convert this to Kelvin, all right? So that means T1 is 23 degrees C plus 273. So what does that equal? I'm not going to be very handy with the math here. 23 plus 273. And that's going to be 296.15 Kelvin. All right, and so we're actually going to have to solve this for T2 in Kelvin first, and then subtract the 273. So let's look at that. So V1 over T1, that's going to be 3.1 liters over T1, which is going to be 296.15 Kelvin. And then that's going to be equal to our V2, which is 22.6 liters, all over T2. All right, and so really what this means is I'm going to get T2 is going to be equal to, multiply both sides by T2. So then I'm going to have to, oh, well here. So what I'd have to do is I'd have to multiply both sides by that. So I would get the 2.6 liters times the denominator here, 296.15 Kelvin. And then this would be over here by itself. So then I would multiply the T2 on both sides and get rid of T2 on that side, and I'd get 3.1 liters times T2. And then I'd divide both sides by 3.1 liters, so 3.1 liters. All right, so what do we get when I do that? I get 2.6 times 296.15, and then I divide that by 3.1. I get 248.38 Kelvin. Now, I need to subtract the 273, so minus 273.15, minus 273.15, and that gives me negative 24.8 degrees C. All right, so that would be our new temperature when we took the balloon out. So it was really cold. I'm surprised folks ain't dead. Anyway, yeah, that's really cold. Anyway, so next up it says you have a gas enclosed in a cylinder fitted with a piston. The volume of the gas is 3 liters, so we have a volume, and you have a pressure of 1 atmosphere. The piston is moved to increase the pressure. Oh, so this is not just a pressure, that's a P1, and this is a P2. What is the volume after the piston is moved? All right, well, here we go then. So we get a V1. So let's go back to how would you derive this relationship? So you got PV is equal to nRT. So we're looking at a pressure volume relationship. So guess what? It's set up the way it already is. So PV is equal to some sort of constant. So that means we can derive this as P1V1 is equal to P2V2. So what do we got here? We've got P1 is 1 atmosphere. V1 is 3 liters. We know P2, that is 5.15 atmospheres. And we don't know our V2. So V2. So that means V2 is going to be equal to 1 atmosphere times 3 liters divided by the 5.15 atmospheres. And we notice that the atmospheres cancels. So we're really looking at 3 divided by 5.15. What do we get here? We get 0.583. Alright, so that's our new V2. Okay, so with that, the volume of the gas is 3 liters. So yeah, it makes sense, right? If you compress it down, right, if you make that same number of moles of gas occupy a smaller space, don't you increase the pressure, right, from 1 to 5? Right? Okay, so if a child releases a 6.25 liter helium balloon in the parking lot of an amusement park, is this another VT? Looks like it. Oh, wait a minute. It's also got pressure in here. Okay, cool. It says if a child releases a 6.25 liter helium balloon in a parking lot at an amusement park where the temperature is 28.5 degrees C, so we have a volume, we have a temperature, and we also know an air pressure. Oh, our temperature and our air pressure are not where they're supposed to be. It says, what will the volume of the balloon be when it has risen to an altitude where the temperature is negative 34 degrees C and 366. Okay, so here's the deal. We have a V1 that is 6.25 liters. We have a T1 that is 28.5 degrees C, but I need to add the 273.15. So let me do that right now because you don't want to forget 28.5 plus 273.15. So that gives me 301.65 Kelvin. And then we have an air pressure, a P1, that is 757.2 millimeters of mercury. All right, this needs to be converted to atmospheres. So it doesn't necessarily, but I'm going to show you. All right. So the way that works, let me write it up here somewhere. Let's see. So 1 atmosphere is equal to 760 millimeters of mercury when we're talking about pressure. So that's all I'm going to do. I'm going to say, all right, well, 1 atmosphere is 760 millimeters of mercury. So I just have to divide it by the 760. So I'm going to get a number that's just shy of 1. So 757.2 divided by 760. That's going to be 0.9963 atmospheres. Okay, now what does it give me next? Next it gives me a new temperature. So it gives me a T2, which is negative 34.35 degrees C. So I need to add that 273.15 to it as well. So let me do that. Negative 34.35 plus 273.15. So it's going to be 238.8 Kelvin. And it also gives me a new air pressure. So P2, and remember all I did was divide by 760, so I'm going to go ahead and do that right now. 366.4 divide by 760, and that gives me a new temperature of a new atmosphere, a new pressure of 0.482 atmospheres. All right, so let's think about what's going on. It's going to want a new volume, so it really wants V2. What pray tell is our V2, our second pressure? So let's go over here for a second. Remember, PV equals nRT. What did they give us? They give us a P1, a P2. They give us a V1, they want a V2. They give us a T1 and a T2. So really I just need to divide both sides by temperature. So I get PV over T is equal to nR. So the number of moles and of course the gas constant, those stay constant. So the relationship I'm looking at here is P1V1 over T1 is equal to P2V2 over T2. All right, now let's derive this to solve for V2, right? Aren't I going to have to multiply both sides by T2 to get rid of it over here? Yes. So I would get T2 there, and then that would go away. And then I would have to divide both sides by P2, right? So then I get P2 down here, and then that will go away. So V2 is all of that stuff, those three on top and these two on bottom. All right, so V2. So we got T2, which is 238.8 Kelvin. We got P1, which is 0.9963 atmospheres. And we got V1, which is 6.25 liters. All right, and then below that is going to be T1, which is 301 Kelvin, 301.65 Kelvin. And then we got P2, which is 0.482 atmospheres. All right, so that's what we're looking at, all that stuff on top. And let's see what cancels. Kelvins will cancel, atmospheres will cancel, and I'll get a volume, right? I'll get liters. So that means V2 here should be 238.8 times 0.9963 times 6.25. Then you divide that by the 301.65 Kelvin. Then divide that by the 0.482 atmospheres. And we get 10.23 liters. So the volume increased, right? So the pressure decreased, so that makes sense for it to increase. The temperature decreased. Yeah, so, well, that one's a little harder to speculate on. But yeah, I think that actually looks decent. Okay, so here, next up, it says for number 5, you have a 1 gram sample of water that vaporizes completely inside a 10-liter container. What is the pressure of the water vapor at a temperature of 150 degrees C? So let's think about what we have. We have a mass of 1 gram of water. Can I get the number of moles of that? I certainly can, because 1 gram of water, right? Water has a molar mass. 1 mole of water is approximately 18 grams, right? It's 16 plus 2, more or less, off the periodic table. So that means, how many moles do I have? What's 1 divided by 18? I don't know right off the top of my head, so calculator it is. So I have 0.056, I'm just going to round it, 0.056 moles of water. So that means I have an N value. I have a V of 10 liters. I don't know the pressure, but I know the temperature is 150 degrees C, which needs to be converted to Kelvin because we keep doing that. So 150 plus 273.15, and that gives me 423.15 Kelvin. Now, it wants the pressure, right? Isn't PV equal to nRT? And we need P by itself. So P would simply be nRT over V. So what do I get? I get 0.056 moles times 0.0821, and I got the liter over atmosphere, mole over Kelvin. I'm just running out of room, so I can't put all that stuff. And then next, my temperature here is going to be 423.15 Kelvin. All right, I ran out of room again. So remember, I said I was running out of room. And then I got the 10 liters. So I'm saying, oh, you can't see what I'm putting in here. So I'm saying, come on, glare, go away. So I'm saying I have 0.056 times 0.0821 times 423.15. Enter. Then divide that by 10. And I get 0.195. So my pressure is going to be equal to 0.195 atmospheres. Because that was the units on R, okay? So that would have been my pressure for that. Okay, I mean, that's a small amount. 0.056 moles is a small amount, right? You don't even have a whole mole of water. So that kind of makes sense. All right, anyway. So from there, hopefully this kind of helps you work through how to look at a lot of these relationships, right? The pressure volume, the volume temperature, and even just using PV equals nRT to solve for one of the 4 variables. All right, but also remember what I do. I always converted my temperature to Kelvin. Always. All right, and you don't have to per se, but I always convert my pressure to atmosphere. I always convert my volume to liter. R tells you the units, so why don't you use them? Come on. As always, stay weird, so will I. Adios.